Hi, my name is Brian Ghigiarelli, and this video presents my database design project for the Spring 2017 course, Principles of Database Systems. In this video, I will cover the design and implementation of my relational database application called FARM, or Fast Advanced Restaurant Management. First, we'll review some of the primary business functions that the application supports in order to keep a small restaurant chain running smoothly during daily operations. Then, we'll review the design for how FARM accomplishes this, including an ER diagram built with the database design principles from this course. Next, I'll show how the FARM application maintains data integrity, including a few advanced edge cases involving database triggers. Then, I'll describe how the FARM implements good security practices with the principle of least privilege around database operations. Finally, I'll introduce the technologies involved in making this application come to life with the least cost possible to the end users by leveraging free and open source technologies. In order to understand the upcoming design decisions, let's review the requirements from the business perspective. First, managers of the restaurant chain want to have insight into the leadership hierarchy and employee trainings in order to properly plan shift coverage. Once the staff is secured, the focus shifts to getting food into the kitchen and out to the customers. FARM enables a dynamic menu by providing real-time tracking of the in-stock quantity of ingredients to show customers the menu items that are available. It helps managers report on the amount and types of ingredients that were ordered, understand what the most popular items are by store, and automatically update the quantity of ingredients in stock when new shipments arrive. All of these operations are available only to the components of the restaurant that need them, but a managerial account should have full override capabilities in order to get the data back on track if needed. This entity relationship diagram, in IE notation, illustrates the inner workings of the FARM database. It was built with MySQL Workbench and follows the design techniques that we'll review in more detail over the next few slides. One of the important things to note is that this diagram indicates identifying relationships and non-identifying relationships among each of the entities. A description of these relationships is provided in more detail in the database report. The design of FARM entities follows third normal form, in which there is no redundancy of records and all attributes of an entity are dependent on the key for that entity. Each attribute has a specific meaning, covered in the report's data dictionary. To that end, FARM does not use artificial keys. All keys are unique and meaningful to the content of each entity. While tracking the current stock of an ingredient for a store, FARM does pre-calculate and store the quantity of the ingredient in a separate entity so that the value can be easily and quickly retrieved for determining the current menu at a store. The quantity of an ingredient in stock at a store could have been calculated by using aggregations across all orders and restocks, but that design would have been a victim of its own success, since more orders and restocks would slow the system down over time. Instead, MySQL triggers keep the stock quantities up to date as related entities are created or updated. Along similar performance considerations, FARM uses indexes on all primary keys and foreign keys in order to ensure that join operations between tables are optimized for speed. This technique allows for yet unknown business queries to run efficiently when pivoting on various entities and attributes. In addition to triggers for keeping business-focused data aligned, FARM uses MySQL's built-in data formats and column types to ensure that data matches the size, range, and format required by the application. This includes decimal values with 2 points of precision after the decimal, as well as date and timestamp formats. Constraints are also used to ensure foreign key integrity so that related entities will be referenced, updated, and removed appropriately. Referential actions, such as cascade, restrict, or no action, are set accordingly to the desired behavior of each table's foreign keys. Security is a first-class citizen in the farm application and is built into the database connection. Each of 4 user accounts available in the database are granted explicit permissions for accessing only the tables that they need. For example, the Orders application can only read the menu and create orders, but it cannot assign employees trainings or shifts to work. Likewise, the Managers application should have overrides for all operations, so has full CRUD access. However, in order to ensure that data integrity is maintained, only the root user can alter tables or low-level database functions. Cost margins are a major concern in the restaurant business, so the farm application was developed on MySQL and Node.js. Both are free and open source tools that do not require a license for production operations at scale. They are also widely used tools that have substantial community support for ongoing maintenance and development concerns. These slides have covered the major design principles and techniques involved with building the farm application. The data definition language and application source code is available as part of the report submission, as well as in a public GitHub repository at the link on the screen. While it's important to understand the design, the implementation details can be just as critical. We'll jump over to Farm's DDL in order to cover some of the implementation techniques involved in making this project come to life. At first glance of the DDL, we see that a full script is available to quickly create the database from scratch, including table definitions, triggers, and column constraints. All tables in this DDL define constraints in line with the columns that they apply to. This allows a database administrator to quickly read and understand the functionality of the system. Additionally, if we scroll to the bottom of the DDL, we see that all entities, from relational tables to triggers and users, are defined in this script. Any future updates to the farm application should be incorporated into this master DDL so that the system can be easily recreated if need be. In order to support rapid development and testing of this application, I used several scripts to quickly drop and recreate the farm database. These basic shell scripts allowed me to iterate on design and syntax, while I ensured that the application and schema matched what the design and business operations needed. The application itself is written in Node.js. The source code includes a suite of more than 100 automated tests that cover nearly all aspects of the restaurant workflow, from employee trainings to customer orders and ingredient restocks. This suite of tests not only tells us that the schema is working properly, but it can also give restaurant owners a sense of confidence that the system will do what they expect it to. As a final note of this presentation, we'll see that the Node test script runs successfully and that all tests are passing. First, we'll drop and recreate the database. Next, we'll take a look at MySQL through the command line to see that the tables are available. Now that we can see they're there, we can go back to the Node application and run the test suite. We can see that we have 116 tests, passing in a matter of less than a second. We are ready for our customers. Thank you for your time, and I hope you enjoyed this database design review.